Our sun, a giant ball of plasma, is a magnetically messy place. It hosts plasma layers in place of its solid surface, and each layer rotates at a different speed. The result is a tangled, turbulent magnetic field that sometimes wells to form sunspots on the sun's surface. These spots are visible indicators of imminent and sometimes intense eruptions from the sun's surface called solar flares. However, the hidden subtleties of the sun's behavior and that of its magnetic field that create and empower these spots have been poorly understood. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. Now, two recently published papers show that tiny flashes occur in the sun's corona, or upper atmosphere, before flares are flung off of its surface. This knowledge would help astronomers understand the physics driving such magnetically active regions. Eventually, these short-lived but bright flashes could be a crucial cue for scientists looking to predict a range of solar flares, from mostly harmless minor ones to the strongest X-class flares that can cause blackouts on Earth and damage satellites. Our results may give us a new marker to distinguish which active regions are likely to flare soon and which will stay quiet over an upcoming period of time, K.D. Lika, an astronomer at Northwest Research Associates in Boulder and an author of both studies, said in a NASA statement. The search to find clues in the sun's behavior that would alert us to upcoming solar flares is not new. But in the past, astronomers focused on the magnetic field's behavior in the photosphere, which is the lowest layer of the sun's atmosphere and the innermost we can observe directly. In the latest research, Lika and her team focused on the upper layers of the solar atmosphere, the central chromosphere, the outer corona that's naturally visible only during a total solar eclipse, and the transition region between the two layers. We can get some very different information in the corona than we get from the photosphere, or surface of the sun, Lika said in the statement. Her team's goal was to find out what differentiates the active, flare-prone areas from dormant ones, and how easy it was to predict a flare knowing those differences. To do so, they used large samples of data collected by NASA's Solar Dynamics Observatory, which provides information about the sun's magnetic field. The Atmospheric Imaging Assembly, an instrument on board the SDO, is a watchful eye that photographs the sun in 10 wavelengths every 10 seconds, each picture at IMAX resolution, recording changes on the solar surface. The instrument snapped pictures daily between June 2010 and December 2018, which made up a large chunk of solar cycle 24. The sun's activity rises and falls in a cycle that usually lasts about 11 years. The observations created a database of 9 terabytes, a single terabyte being 1,000 gigabytes, that included close to 20 million images taken in ultraviolet and extreme ultraviolet wavelengths, which marked the appearance of active regions on the sun's surface and tracked their evolution into flares. It's the first time a database like this is readily available for the scientific community, co-author Karen Dissauer, an astrophysicist also at Northwest Research Associates, said in the same statement. It will be very useful for studying many topics, not just flare-ready active regions. Scientists group solar flares into 5 classes based on the intensity of their X-rays. The most powerful are X-class flares, M-class are smaller but still major events, then C and B classes, with the smallest A-class solar flares too weak to impact Earth. As one example, Lika's team focused on a weaker C-type flare that occurred on August 3, 2011, and compared images taken over 3.5 hours, showing the region's transition from quiet to flare-prone. The scientists found that the two images look fairly similar except for a small localized brightening that was the only easily identifiable difference that might herald an imminent flare. Lika's team is focusing on part of the database that includes 7 hours and 13 minutes of images taken daily in ultraviolet and extreme ultraviolet wavelengths, hoping to study both short-term changes and long-term trends for each active region in the database. With this research, we are really starting to dig deeper, Dissauer said in the statement. Down the road, Combining all this information from the surface up through the corona should allow forecasters to make better predictions about when and where solar flares will happen. A green flash is a phenomenon in which part of the sun appears to suddenly change color for about 1 or 2 seconds. The brief flash of green light is seen more often at sunset than at sunrise. This fleeting spectacle is caused by the refraction of sunlight, which is particularly significant at sunset and sunrise, when the light travels through more of the Earth's atmosphere. The atmosphere bends the sunlight passing through it, separating the light into its different colors, much like a prism bends and splits sunlight into rainbows, according to Cornell University. The various colors of light bend different amounts based on their wavelengths. Shorter wavelengths, blue, violet, and green, refract more strongly than longer wavelengths, yellow, orange, and red. As such, blue and violet light are scattered by the atmosphere while red, orange, and yellow are absorbed, leaving the green light the most visible during the few seconds when the sun sets below or rises above the horizon. Sometimes, when the air is especially clear, enough of the blue or violet light rays make it through the atmosphere and create a blue flash instead of a green one. Nonetheless, green is the most common hue reported and captured in photos. There are 4 categories of green flashes: inferior mirage, mock mirage, subduct flash, and green ray, according to an article published by the American Association for the Advancement of Science, AAAS. Nearly all green flash sightings fall into the first 2 categories. Inferior mirage flashes are oval and flat and occur close to sea level when the surface of the water is warmer than the air above it. Image album, Strange and Shining, Gallery of Mysterious Night Lights. Mock mirage flashes, on the other hand, occur higher up in the sky and when conditions on the surface are colder than the air above. The flashes appear to be thin, pointy strips being sliced from the sun, and they last about 1 to 2 seconds. Subduct flashes are created when the sun appears to form an hourglass shape due to a phenomenon called atmospheric inversion, which occurs when a layer of warm air traps cool air and moisture close to the ground. In this rare circumstance, the upper section of the sun may appear green for up to 15 seconds. The rarest type of green flash is known as a green ray. In this instance, a beam of green light shoots straight up a few degrees from the green flash immediately after the sun sets for about a second. It's caused by the combination of hazy air and an unusually bright inferior, mock, or subduct green flash. How to see a green flash? While there isn't an optimal condition that will guarantee a green flash sighting, the best way to potentially observe one is to go somewhere that provides a clear view of the horizon and is free of pollution, such as over the ocean, according to Young. Green flash sightings frequently occur at the ocean, where more of the atmosphere is visible and the line of sight is virtually parallel to the horizon. Flat prairies and deserts also tend to have the appropriate conditions for a green flash sighting. Sometimes, conditions are so perfect that a rare double green flash can be observed. Polar explorer Admiral Richard Byrd and his crew claimed to have seen a green sun persist for 35 minutes while on an expedition to Antarctica in 1929, according to Young. Scientists now believe that there must have been some mirage effect present for the phenomenon to go on for that length of time. Scientists have been studying solar flares for years and have tried to predict when and where one will explode from the boiling hot surface of the sun, and now new clues have been discovered that may help with those predictions. Researchers from the Northwest Research Associates, NWRA, used data collected from NASA's Solar Dynamics Observatory, SDO, to identify small signals of the sun's atmosphere, the corona, that will help to determine which regions on the sun were more likely to produce solar flares.